Einstein Public Lecture this evening. Sarah Hart is Professor Emerita of Mathematics at Birkbeck College, part of the University of London. And she's also a fellow of Gresham College, London, where she recently served a 4-year term as the Gresham Professor of Geometry. This is a big deal. This is a position which has existed since 1597. It's the oldest professorship, I believe, in the United Kingdom. She was the first woman to hold the title, and I encourage you to explore the nature of Gresham College. It's a remarkable institution. Has how many undergraduates?
0.
0 undergraduates. How many graduate students?
0.
0 graduate students. How many faculty?
7.
7 faculty. That's a great faculty-student ratio. Sarah was educated at the University of Oxford and earned a PhD at the University of Manchester Institute of Science and Technology in Group Theory under the direction of Peter Rowley. Rowley. She's published extensively in the area, and I'm particularly interested in her work on various types of product-free sets and groups, which relates closely to some of my work on sum free sets in additive systems. But more recently, and what work you're most famous for, she's the author of Once Upon a Prime, The Wondrous Connections Between Mathematics and Literature, for which she deservedly won the 2024 Euler Prize from the Mathematical Association of America. This fantastic book explores the myriad connections between mathematics and literature. Buy it. It's great. So it gives me immense pleasure to present to you Professor Sarah.
Thank you. Thank you. So yeah, I was really honored to be invited to give this lecture. I think it's so important, you know, for mathematicians in the audience. We know it's important to tell and share about our work and how wonderful and beautiful mathematics is. So I'm delighted to have the opportunity. And I know that in the audience, there's kind of every type of person from like extremely brilliant professor to perhaps people who are starting their mathematical journey. So, and also it's the last talk of the day. So I'm going to keep it light and we're going to go on this journey through literature. I'm going to begin though by just noticing we do not often see the words mathematics and literature together. We kind of, you know, the perception of mathematics is often that it's really, really useful for science, right? So it's in with science in the way that we think about it. And there's an excellent reason for this. You know, we talk about mathematics as being the language of the universe. That's exactly right. And it's because the universe is full of structure and symmetry and pattern. And mathematics is the best language we have to describe and explore and understand those beautiful things. So absolutely, mathematics is a vital tool for science. But, you know, we're human beings. We are creatures of the universe. Our minds delight in pattern. We love it. We love structures and patterns. We love symmetry. So it's totally natural that mathematics will be relevant for our forms of creative expression, like the rhythms in music and the symmetries of art, and, as we'll see, the structures and patterns in literature. So this is a completely natural thing to have mathematics and literature together, and I hope that by the end of this talk, you will all agree about this and we'll be able to look at literature in a new way. So let's begin by thinking, if I'm saying, you know, there's structure and pattern in literature, the place where it is most perhaps visible, closest to the surface, is in poetry. Because while it's rather difficult to give a definition of poetry, any form of poetry will have some kind of structure to it, some sort of constraint, because if it doesn't, then it's prose, right? So, for example, there's a precise numerical constraint behind several forms of poetry. The haiku form has exactly 17 sounds or syllables to get from setup to payoff, right? So the poet who is writing the haiku has to really, really think carefully about every single sound is going to count here. And it's a beautiful way to encapsulate a thought. You know, and actually there's a bit more structure because those 17 syllables have to split into a 5 and a 7 and a 5. So yeah, all prime numbers there, which is kind of interesting. So this is one kind of restriction, one kind of constraint that we could define in poetry. But there are lots and lots of others. And in Western poetry, we quite often have something like a meter, so the rhythmic pattern of the words, those iambic pentameters that beloved of Shakespeare, that's the kind of pattern that we could talk about. There's also the rhyme scheme. So many traditional forms of Western poetry have a rhyme scheme. And I'm showing you here as just an example. This is one of Shakespeare's most famous sonnets. Every sonnet has 14 lines, and then certain lines must rhyme with each other. Sometimes you have to pronounce them in Elizabethan English to make that work, but they should rhyme with each other. So that A, B, C, D thing, those are indicating which lines must rhyme. So it's sort of a constraint, a definition of what the pattern is going to be. So here we've got that A, B means the A lines rhyme with each other, so lines 1 and 3, and indeed summer's day does rhyme with buds of May, right? So this is the rules, the setup, the axioms, if you will, of a sonnet. Now, just as in mathematics, having a pattern, a structure, a constraint does not stop you being creative. You know, we can use these things as a spur to our creativity. If we say we want this particular structure, then it actually helps us to be creative, to think about how we can express our idea. A story, you know, a tale of love and comparing your lover to summer. And you express that idea in 14 lines with these rhymes. And in mathematics, we do the same kind of thing. You know, we set up some ground rules according to whatever we want to do, if it's a puzzle we're making or if it's the axioms of Euclidean geometry. And then within those rules, we have a playground to explore and be creative. So within the rules of Euclidean geometry, we can prove Pythagoras' theorem. And within the rules of the sonnet, Shakespeare can write, "Shall I compare thee to a summer's day?" These things are creative playgrounds for us to explore. Okay, so now quiz question. Which poet has written the most sonnets? So Shakespeare wrote quite a lot. Some counts say 154. Anyway, it's a lot. But I'm sorry, Shakespeare, that's nothing compared to Monsieur Raymond Queneau, who produced a little book in 1961, whose title translates as 100 trillion poems. And the poems are sonnets. So this is an example, and we'll talk about how he could possibly have done this. If you understand the structure and you know what the patterns are, then you can exploit that structure to do something interesting and new. So this book, spoiler, it's not 100 trillion pages long. That might be a little pricey for the market to bear. So how does he do this? Well, if you get hold of the book, it appears to just have 10 sonnets in it. 10 14-line sonnets over 10 pages, right? But then Queneau does something very clever. So each sonnet respects the sonnet rhyme scheme. And then all of the first lines of the sonnets rhyme with each other. All of the second lines rhyme with each other. All of the third lines rhyme with each other, and so on. So that means you can make new poems from your existing kind of generators. You can take any one of the first lines and follow it with any one of the second lines, and so on. And actually, some versions of the book allow you to do this physically. They're like a little sort of flip book, right? So you can physically arrange the pages in such a way that you have made the poem you want to make. So then, how many potential poems are there in this book? Well, there's 10 choices for line 1, times 10 for line 2, times 10, times 10, times 10, times 10, 14 10s multiplied together. And if you count up all the zeros and work that out, that's your 100 trillion. So it's a really cool idea. And, you know, for me, this is like, he's created a 3-dimensional rhyme scheme here, which is very nice. There is a question sometimes we might raise about this kind of thing, though, and I think it's valid to ask. You know, this is really, really clever, but, okay, is it art or is it just artifice? You know, there has to be something that makes this literature, and it's not simply a very clever thing to do. That's not quite enough. For me, this makes the grade. It is literature because not only is it really clever and fun, but it raises actually quite interesting questions about the nature of, you know, authorship, creativity. Do these poems actually exist? I mean, are there 100 trillion poems in this book, right? Can Raymond Queneau have written 100 trillion poems if he hasn't even read them? Like, and okay, he has not read all of these poems. Here's how I know. If we were to start now, and we're going to read all of these sonnets, and we're going to go quite fast because we want to get to the reception. So we're going to do one sonnet every minute, starting now. We're going to be here a while. I'm sorry to have to break, you might have to change your travel plans. So we're going to be here, you can work this out, for 190 million years, a little bit over. And that's, yeah, we can't do this. No one can read all of these poems. So did Queneau write these poems? He hasn't even read them. No one's ever read them. And also, then, if we are choosing which lines to use, like we've had some creative input, but we can't say we've written the poem we make because Raymond Queneau wrote every single word of every single line. So how does that work? And this is extremely pertinent right now in the world of ChatGPT and large language models. You know, have they written a poem? If they read every poem on the internet and then produce something, like where does the attribution of intellectual copyright go there? These are questions we're asking right now. So for me, this is just a lovely lens through which to view these questions. We can do a little bit more, though, with poetry and structure. And since we have some mathematicians in the room, I thought I should tell you about an example of a kind of poetic form which has a lovely structure, which actually has led to mathematical research and new theorems. And it's the sestina. So the sestina is a beautiful kind of form of poetry. I'm showing you the first verse of a very well-known sestina by Elizabeth Bishop, A Miracle for Breakfast. It's a beautiful poem. I'm not going to do it justice in this talk. So if you've never seen this poem, I do encourage you to go ahead and read it kind of at your leisure in a calmer setting. But I'm going to tell you what the structure of these kinds of poems are. So a sestina, that word comes from the word for six. The structure of it is, it's got 6 verses, each of which has 6 lines, and it doesn't have a rhyme scheme. Instead of a rhyme scheme, it uses the same 6 words at the end of the lines in each verse, but in a different order. And that order changes in the same way from each verse to the next. So I'll show you what that permutation, that shuffling is. So if you have the end words, so in this example, it's the end word that's like coffee and crumb and balcony, right? So it's those end words that are changing their ordering. So if you start off with the order 1, 2, 3, 4, 5, and 6, then the shuffling arrangement you do, you can think of it as starting from the end and working backwards, 6, 5, 4, and then you interleave that with starting from the beginning and working forwards, 1, 2, 3. So in the next verse, the words would come in the order 6, 1, 5, 2, 4, 3. So here, in this example, we've got coffee, then crumb, then balcony, miracle, sun, and river. That's the order in the first verse. So to make the order of those words in the second verse, we start at the end, so river, and work backwards, sun, miracle, and we interleave with coffee, crumb, balcony, right? So you get, there's river, sun, miracle coming backwards, coffee, crumb, balcony coming forwards, and then we interleave them. So we've got river, then coffee, then sun, then crumb, then river. So you can see that's the order of those words in the second verse. So it's not quite rhyming, but there's some resonances from one verse to the next. And then for verse 3, you've got this new ordering now. You do exactly the same thing to work out what the order should be for the third verse. You keep going, and this is now verse 6. By this point, we've kept repeating this process, and we've got this particular order, right? Now, I've said there are 6 verses in a sestina. It's kind of 6 by 6 by 6 sort of structure. If we were to try and make a verse 7, doing this same process, what do? We work backwards from the end, so it would be coffee, then balcony, then sun, and we interleave with working forwards from the beginning, crumb, miracle, river, right? So it's going to end up as coffee, then crumb, then balcony, then miracle, then sun, then river. And if you are very eagle-eyed, you will notice that's the same order that we started off with. So actually, there isn't a verse 7, but somehow there's this lovely completeness to this process because we've got all the possible places we can get to by repeating this process. And every single word appears exactly once at the end of every single line, and you do the complete thing. And then if you were to carry on, get back to where you started. So it's got this lovely feeling of completeness to this structure. It's very, very nice. Now, typically, a sestina usually will kind of finish off and tie it up with a lovely bow by having a final little 3-line part where each of the 6 words appears somewhere in that. So it shows you that this is the end of the poem. So mathematicians see sestina. It's got this 6x6 sort of structure to it. And a natural question to ask is, well, would this work if it wasn't 6s? Would it work for my favorite number? And as mathematicians, our favorite number is n. Does it work? Can we write an n-ina, right? What would that mean? That would mean we'd want n stanzas, each of which have n lines, and then those n end words would be sort of shuffled around in this way, and we want it to all work nicely, just like a sestina. Every end word should appear exactly once at the end of each line, and no sort of horrible repetitions. So well, we don't know. This is, again, in mathematics, we almost always don't know, and we almost always can't do it, so we almost always try a few small examples. So let's just randomly try n equals 4, right? Can we write a quartina? So let's pick some, I was trying to think 4 words that go together. Let's imagine our end words are north, east, south, and west, okay? So let's do this sestina-like shuffling. What do? We start at the end and work backwards, right? So west, interleaving with starting at the beginning and working forward. So it would go west, then north, then south, then east. That's the end words of verse 2. Okay, what about verse 3? So again, do the same thing, start at the end, east, and then we'd go west, and then we go south, and then we go north. Those are the words for verse 3. Okay, what about verse 4, the final verse? What's it going to look like there? So start at the end, north, and we're working backwards, and then interleave with starting with the beginning. So it would be east, and then it would be south, and then, oh dear. Oh dear, it would be northeast, southwest. Unfortunately, we've already got back to our starting verse, right? We only had 3 different verses, and the 4th one, we already got back too soon. So this doesn't work for that reason, but also, you've probably noticed, there's another horrible thing, which is that south never moves. That 3rd word just boringly sits in the same place. So this is just a total disaster. 4 does not work. So, of course, we don't give up. We're discouraged, but we don't give up. We try other numbers and we play around. And mathematicians did this and came up with, actually, an answer, a classification for exactly the numbers that could produce this n-ina type pattern. Now, the details of it are a little bit technical, but there is one kind of number which it's guaranteed to work for. This structure is guaranteed to work. Now, the condition I'm about to tell you is not, it is sufficient, but it is not necessary, right? Because the numbers I'm about to talk about are prime numbers. 6 is not a prime number, I've noticed, but 6 does work as well. So this doesn't tell you all of them, but there's some numbers that are guaranteed to work, and they are Sophie-Germain primes. So Sophie Germain, brilliant French mathematician. It's quite cool to talk about. It's International Women's Day today, so it's nice to have an international woman on the screen. So Sophie Germain was a brilliant mathematician. Some of her work was around trying to prove Fermat's last theorem, which obviously would not turn out to be proved in its entirety until the 1990s, but she managed to prove it in some special cases. And some of those special cases were these particular prime numbers, which are now named for her, Germain primes. So a number is a Germain prime number if it is prime, and when you double it and add 1, it's still prime. So 3 is a Germain prime because twice 3 plus 1 is 7, which is also prime. But 7 is not, because twice 7 plus 1 is 15, which isn't prime. Okay, so this structure, there's a theorem that says this structure is guaranteed to work. You can make an n-ina if n is one of these Sophie Germain primes. So you can write a 3, a tritina, and you actually you see these in print every so often. They definitely have been done. But you can also write an 11-ina. I don't know what the Latin for 11 is, an undeca-ina or something. That's mixing Greek and Latin. That's terrible. Forget I said that. Yeah, so you can do it for 11 because twice 11 plus 1 is 23 is prime. So, the field is wide open. If any of you are kind of bored over spring break and you want to write a 23 ENA, you are guaranteed that it will work because of this lovely fit. So that's quite nice. We've got a poetic form, and actually you can turn it into doing some lovely mathematics. But structure and pattern are not just present in poetry. I want to give you some examples where actually we find mathematical ideas and structures and patterns in books more generally, in literature more generally. And for me, in fact, literature itself has inherent structure, rather like in geometry. So in geometry, we have this hierarchy of points make up lines, lines make up planes, and so on. Well, in literature, letters make up words, words make up sentences, sentences make up paragraphs, and then chapters, and then volumes. So at each level of this geometric kind of hierarchy, the author can choose to impose additional constraints or structures and see what will happen. So there are, for example, examples of books that have been written entirely without the use of one or more letters. There's a very famous book called La Disparition, which does not have the letter E in it anywhere. That's quite a challenge. Even more of a challenge for the person who translated that into English, which is like another layer of things. But the level of structure I want to talk about is the chapter, level of the chapter. And the book that involves this is a mathematical constraint we're going to talk about is the luminaries. So this is a book by Eleanor Catton. It came out in 2013. It won the Booker Prize that year. So it's a fabulous book. It's got everything you could want from a plot. Right? It's set in a gold rush town in New Zealand in the 19th century. It's got love and intrigue and opium and murder and stolen gold and just a mystery. It's great. One of the major themes of the book is the interplay between choice and fate and free will and destiny and the tension between those things, how much we're in control of what happens to us, how much we're just being buffeted around by forces we don't understand. So to tie in with that, Eleanor Catton uses a lot of astrological themes in the book, sort of metaphors. That's not the maths bit, by the way, but she has 12 key characters, for instance, who are loosely associated with the 12 signs of the zodiac. And their actions are in some way determined a little bit for them by that thing. The luminaries of the title, that's the sun and the moon. They're the lovers in the story. And then the mathematical constraint I want to talk about is that to mirror the 12-ness of the 12 characters and the 12 signs of the zodiac, the book is divided into 12 sections or chapters. And then to mirror the waning of the moon, each chapter, it's a mathematical bit, is exactly half the length of the one before. So this is a strong constraint. So we're going to get a kind of halving and halving and halving. Visually, I can show you exactly what this does to the chapters. Here's chapter 1, right? Chapter 2, half the length. Chapter 3, half again. Chapter 4, chapters 5, 6, 7, and 8 slot in nicely. Chapters 9, 10, 11, and 12 in there. So we're creating this beautiful spiraling in effect. When you read the book, I mean, nowhere does it say out loud, this is what's happening. But when you read the book, even if you don't necessarily know the precise thing that's happening, you feel this, you experience it when you read as the chapters are getting shorter, the pace is picking up, like the gear wheels are tightening, and the spiral is closing in. By the time you get to that very last final 12th chapter, it's just a short conversation between the lovers. It's set chronologically somewhere in the middle of the action. So what we know and they don't yet know is that their fate is sealed. They are trapped in that spiral. So it's a really great structure for the book that gives you this feeling as you go along. We can be a bit more specific about exactly what the implications are for the length. So you can already see from this picture that actually the first chapter takes up more than half of the book. Okay, more than half of the book. We can be a bit more detailed. If we think of that very last, shortest chapter, let's give it a length. Let's say it's S for shortest, words or pages, doesn't matter, just let's say it has length S. then we can work out the length of all the other chapters, right? Because we just work backwards, doubling and doubling and doubling. So twice, 4 times, 8 times, and so on. 11 doublings back, we get to the first chapter. So the length of that first chapter is the shortest one multiplied by 2 to the power 11, which everyone will know is 2048. So that first chapter then, I mean, it's really very, very much longer than the last one. Every word that Eleanor Catton writes in chapter 12, she has to write more than 2,000 words in the first chapter. So that's quite an ask. She's got to be careful. We can also use this if we want to work out the total length of the book. And luckily for us, we don't need to do it. Mathematicians are basically lazy. We don't like to have to do things one by one by one. There's a nice little rule about adding powers of 2. If you add up the first few powers of 2, 1 plus 2 plus 4 plus 8, and so on, the answer is the next one, take away 1. It's very nice. So we can add up all of these without actually doing it, which is always good. If you add up all of the powers of 2 up to 2 to the power 11, the answer is going to be the next power of 2, take away 1. So the total length of the book, in terms of this last chapter, you just multiply it by 2 to the power 12 minus 1. Now, that's very nice. I wanted to show you this because another kind of query that one might have quite naturally is, you could say to me, listen, Sarah, you're a mathematician. You love maths. You love structures. Sorry, math. You love math and structures and patterns. So you're going to see them everywhere you look. But, the author isn't really thinking about this so much. I think I can prove to you she is. She knows this. She knows that 2 to the power 12 is vital to the structure of this book. And here's my evidence. Remember I said in the plot of the story, there's some stolen gold. So there's a court case around this stolen gold in the book, and its exact monetary value is stated. And that value in pounds is 4,096, which you might notice is exactly 2 to the power 12. So she's given us that little present. If you're reading that book and you see 4,096 pounds, it's a bit, oh, that can't be a coincidence. And it's not. That stolen gold is sewn right into the fabric of the book. So it's really nice. And yeah, she absolutely knows about this and what's going on. Now, this is an example of a structure. It's a fairly kind of simple halving and halving and halving, very effective. I want to give you one more example of a structure in a novel. And the story of this structure goes back a few centuries to puzzles like this. So this doesn't look like a puzzle, but it will when I tell you what's going on. So this was entertaining the French aristocracy in the winter evenings a couple of centuries ago. So what you do is you take standard deck of cards and you take the 4 highest valued cards in each suit. So the Jack, Queen, King, and Ace of each suit. So spades, hearts, clubs, and diamonds. So that gives you 16 cards. And then you have to arrange them in a square, like I'm showing you. This is one solution, but I haven't spoilt it forever because there are lots of other solutions for you to find. So you have to arrange them in a square. It's sort of like a Sudoku type of thing, because you have to have in every row and in every column, one of each value, card value, and in every row and every column, one of each suit. So in every row and every column, there should be one king. Every row and in every column, there should be one diamond, for example. So that's the challenge. This is one solution. There are many others, many, many others. So you can play around and try and find, I won't say all of the solutions because there's hundreds, but try and find some. But after a while, you'll be like, okay, I can do this. I'm no longer like super excited to try and find more of these. So you want a bigger challenge. And just such a bigger challenge came along a few decades later in the court of Imperial Russia, where everybody was trying to solve the 36 officers problem. This is a harder challenge. It's essentially the same problem, but just like an order 6 version of it. So the problem says you have 36 army officers, and they're divided into 6 regiments and 6 ranks. So like in each regiment, you've got 1 soldier of each of 6 ranks. So that gives you 36 officers in total. And can you arrange them this way so that in every row and in every column, there's 1 officer of each regiment and 1 officer of each rank? And I have to make explicit something which is implicit with the card puzzle, and that is that every possible pair happens exactly once. So you have, one major from the red squadron or something, right? So every pair occurs exactly once, like you have with the physical cards. With the cards, you don't have two aces of spades. So that's the challenge. It's like an order 6 version of the card puzzle, and no one could do it. Right? The card puzzle has loads of solutions. No one could seem to do the 36 officers problem. So everyone was talking about struggling with it. Even Catherine the Great, Empress Regnant of all Russia, couldn't do the 36 officers problem. So if you're the Empress, what do? You say, bring me a mathematician and get them to sort it out. So luckily for them, there was a mathematician in St. Petersburg at the time, and it was one of the greatest mathematicians who ever lived, the master of us all, Euler. So Leonhard Euler is instructed, sort this out, right? The thing is, he couldn't do it either. So when Leonhard Euler can't do something, maybe it's impossible, okay? So of course, being a mathematician, he starts to immediately think, right, this is just this is the order 6 version of a more general question. The card puzzle is the order 4 version. He called these things, because you've got two things. It's like cards, it's suits and values. With the officers, it's regiments and ranks. So when he was trying to work this out in more generality, again, can I do it for n? He labeled one thing with like the Latin alphabet, one thing with the Greek alphabet, and he called these things Greco-Latin squares. And actually the Latin squares that many of us in the room are familiar with, that's a back formation from his initial Greco-Latin squares. They've got lots of different names. I decided I will call them orthogonal Latin squares, but there are about 12 different possible names for these things. But this is what we're talking about. Euler says, for what numbers can I do this? For what sizes is this possible? It's definitely possible for 4. He didn't think it was possible for 6. He found ways to construct these orthogonal Latin squares for odd sizes, so 1, 3, 5, 7, and so on. He said he found a way to do it when the size is a multiple of 4. So 4 like the card puzzle, and then 8, 12, and so on. So what are the numbers that are left? They're the even numbers that are not multiples of 4. 6 is one of those. He thinks that's impossible. 2 is the first one. Actually, you can just physically look at this. There's only a couple of ways you can put this thing together, and neither of them work. So 2 is definitely impossible. 6, no one seems to be able to do. And so he made a conjecture. The conjecture is you can always make these things for any size unless your number happens to be 2, 6, 10. So those numbers that are even but not multiples of 4. Okay, so 2, you can easily check. It's definitely impossible. 6, it was eventually proved by a French mathematician called Gaston Tarry, who in about 1905, I think, in what's aptly known as a proof by exhaustion, showed that there genuinely is no solution to the 36 officers problem. These structures do not exist, order 6. Okay, so it's looking good for Euler. Until 1959, when 3 mathematicians found order 10 orthogonal Latin squares. They exist. And this was big news, right? It was on the cover of Scientific American in November 1959. Euler's never wrong. So this is like very exciting. His conjecture was false, and the order 10 orthogonal Latin squares exist, where you've got these, these two kinds of things here. It's we're being shown like you've got 10 different colors, and then you've got the little squares also with 10 different colors. So that's the way it was shown in a rather appealing way on the cover of Scientific American. These things exist. And in fact, it's worse than that because, well, or better, depending on your viewpoint, actually all of the other numbers are possible. 14, 18, everything else is possible. So poor old Euler, like what he could actually see, 2 and 6 really are impossible, but then everything else works. So this is like one of the now mathematicians, we constantly fail. Constantly, we make conjectures and they turn out to be wrong. Every so often we get lucky and we can prove a theorem. But Euler, was one of the greats, and we remember more of his successes. So this is a big story. And so if you are writing a novel about failure, what better structure to use at the heart of your book than order 10 orthogonal Latin squares. The emblem of one of the few times Euler failed. And this is exactly what Georges Perec did in his book, Life a User's Manual, 1978. He set this book, this novel, in a Parisian apartment block with 100 rooms, a 10 by 10 array. And every chapter of the book was set in a different room. And the way that he used this lovely structure was to give each chapter its own unique flavor. And how he did it was he had lists of 10 attributes. So it might be colors, 10 colors and 10, let's say, fabrics. And then using this orthogonal Latin square structure, he was able to put each pair of those things in exactly one of the rooms. So there's exactly one chapter that would have, I don't know, yellow velvet. There'd be exactly one chapter that would have green silk, right? So every pair occurs in exactly one chapter, and so each chapter has its own kind of feeling to it. Every room has its own unique feeling. So this is quite nice. And this book, so it has, one of the themes is like how we try and do things, but sometimes we're thwarted and we can't quite manage it. So there's a character, for instance, who is trying to, for reasons best known to himself, construct 100 jigsaw puzzles. And unfortunately, he dies just before he can put the last piece of the last puzzle in. So there's a lot of those kind of things going on. And then at the heart of it, this Latin square structure, which Euler didn't find. But there's another little bit of mathematics in here, which is if you've got a 10 by 10 array of rooms, actually, what order are you going to put the chapters in? So there's a mathematical answer that Perec chose. The stories, the chapters follow a knight's tour of a 10 by 10 chessboard. That's really nice. But did I say one of the themes of the book is failure? This knight's tour is not complete. The book has 99 chapters. And he's very cheeky. He blames one of his own characters for this. He blames a little girl in the book who must have skipped past one of the rooms as she went by. So yeah, it's a knight's tour, but it isn't quite finished. So he plays around with this structure. It's very, very, very cool. So then so far I've talked about structure and pattern and how we can see it in literature and how, for me, knowing what's there and how it fits together, that just makes me enjoy the literature even more. So it's all bonus. The maths is good, the literature is good, and together they're fantastic. But there are other ways in which mathematics and literature can have a conversation. So once you've got your structure decided, you still have to write the words, right? You still have to actually write a piece of literature. And when you do that, when you use language, you use metaphor and symbolism and allusions, and often they are mathematical. So when I say this, I mean, there are, Tolstoy uses calculus metaphors in War and Peace, yes, but even at a much more elemental level, there is mathematical symbolism in the most simple of stories. And that's the fairy tales and the folks' tales and the religious stories that we grow up with. I'll just give an example from the kind of thing. I grew up reading about fairy tales like Goldilocks meets 3 bears, Snow White meets 7 dwarves. Those young ladies walking through the forest late at night, they are the 12 dancing princesses. And gosh, I'm scarred for life because my little girls had the DVD of Barbie and the 12 dancing princesses, and they all had individual names, and we all had to learn all of their names. But okay, you've probably been spared that, so I won't say any more there. But fairy tales, and actually lots of the stories, folk stories, are full of numbers, full of numbers. I'm going to say something about the number 3, because I think that's probably the most important for narrative. It's not just Goldilocks that has a 3 in it, 3 bears. I mean, you've got the 3 billy goats gruff, and you've got the good fairy always gives you 3 wishes. So does the genie, 3 little pigs. There are so many 3s in fairy tales, but also in the language that we use. In our language, we have lots of three-word phrases, three-letter abbreviations. We have, often in our ways of division or dividing things or categorizing things, we tend to put things into threes, small, medium, and large. Or when we're running a race, right, we start with a three-word phrase, ready, set, go. And at the end, the top 3 people win 3 medals, bronze, silver, and gold. And then we say hip, hip, and hooray. You know, it's endless. Once you start seeing threes, you never stop seeing threes. But in narrative, for me, there's a kind of geometrical reason why these simplest kinds of stories often have threes. And it's like this. So imagine a generic fairy tale. 3 brothers are going on a quest. Now, in this, typically, we'll all have encountered a story like this. And, you know, the oldest brother, he thinks he's great. He's very pleased with himself. He goes off on the quest and he fails, right? So we've got a point in space now, 1 data point. Okay, you know, nothing much to go on. Then the second brother, who also thinks he's great, he goes off on the quest and he fails. Now you've got 2 points. When you have 2 points in geometry, that defines a line. You have a line, you have a direction of travel, you have an expectation. And then the third, youngest brother, overlooked, very humble, you know, he's the good one, really. He succeeds. He succeeds. So you've come away from the line, gone up a whole dimension in complexity. You've created a shape, you know, in geometry, 3 is the smallest number of points you need to define, to get off that line and go into like 2-dimensional world and create a shape, a triangle. And in narrative, 3 is the smallest number of times you can repeat something in order to first set up an expectation and then subvert it. And that for me is why 3 is such a powerful number in narrative, especially in these most simple kinds of story, where, you know, you have to have enough to have a nice surprise at the end. And actually, jokes as well. Often there are many kinds of jokes that involve 3s. So, you know, pick your favorite cultural stereotype, and we all have heard these jokes, where there are 3 people and like 2 of them are sensible, and then the third one isn't. So then they're presented with some scenario, and the first 2 people do something sensible, and then the third one unexpectedly does something silly, and that's the joke, right? So it's the same thing that's happening. So numbers, yeah, everywhere in fairy tale and folk tale. And there are, I think, mathematical reasons, at least contribute to why some of these numbers have this sort of resonant power. I'm going to give you a slightly more higher level example of a mathematical metaphor or illusion in literature, and it's in Moby Dick. So I love Moby Dick because this was the book that started me off on this whole journey really into thinking more seriously about mathematics and literature. So I'm someone, I'm sure many of us are, who just always from my earliest years had my head in a book. I would always read just anything that I could see I would be reading. So, you know, at breakfast time, I'd be reading the back of the cereal packet. If there was nothing else to read, I would just always be reading constantly, still am. And so throughout all those years, when I was also becoming a mathematician, I would notice things, and I'd find them interesting, but it wasn't until I read Moby Dick and was absolutely amazed by the sheer number of mathematical illusions and the kind of glee, you know, the excitement you can see when you read this. It's so obvious that Herman Melville enjoys mathematical ideas, and they come out in his writing. No one's making him do that. It's clearly just part of the furniture of his mind. You know, he likes these ideas, and so he's thinking about them, and they come out in what he writes. So Melville's writing is full of mathematical illusions, and they're fun, and he's enjoying them. And that's completely natural, right? And I don't know, we perhaps have lost that a little bit, but it's so natural to enjoy mathematical ideas because they're fun. So when I read this novel, I thought, oh, this is brilliant. I'm going to now, because I'm an academic, I'm going to go and just have a look at all the academic papers that there will definitely be about how mathematical Herman Melville is. And then I couldn't really seem to find very much. So then, well, I'd better write a paper. So I did. And then that's sort of how I got into this, really thinking more seriously about literature and mathematics. So the illusion, the metaphor I want to talk about, oh, it's not a metaphor, it's an illusion that Melville makes in Moby Dick, is he references this curve, which is the best curve that there is, and we can argue about this later, but it is the best, and I'm right. It's the cycloid. So the cycloid's such a lovely idea. It's a really simple question. You say, roll a wheel along a road, follow a point on the rim of that wheel, and just look at what path that makes. And you get this arch being repeated. That arch is called the cycloid. So it was Galileo that gave it its name. And every mathematician, in the 16th, 17th, 18th century, every mathematician we've heard of, and probably lots of others, was fascinated by the cycloid. And the reason is that it's got some really lovely properties. So it's a simple idea. You can all sort of understand how it's made, but then you ask questions. So, when we learn about circles, we learn the formula for the circumference of a circle and the area of a circle. So when you meet a new curve, you say, okay, well, what's the length of that arch? What's the area underneath it? And these were difficult questions, and people struggled over them and became fascinated by this curve, trying to understand its properties. When I say all sorts of mathematicians, here's just a few names who studied this curve and were fascinated by it. It got the nickname the Helen of geometry. So as in Helen of Troy, really a beautiful thing that fascinates lots of people. That picture there, that's the statue of Blaise Pascal in the Louvre Gallery in Paris. And I don't know if you could see the resolution of this picture, but what he's looking at there, for all eternity, he is studying the cycloid. He found it fascinating. He said that, in fact, that it brought him back to mathematics. He'd sort of sworn off mathematics, thinking he really ought to spend all his time on theology. But one day he had a terrible, terrible toothache. And to distract him from the pain, he thought of the most enticingly exciting thing that came into his mind, which was the cycloid. And this worked. And he forgot about his toothache, he forgot about the pain, and it was because of the cycloid. So he took this as a sign from above that it's okay to do mathematics, and it is. So he studied this curve, he found lots of good properties, and so did many other fabulous mathematicians. Helen of Troy was, very appealing to people, but she also did cause some squabbles, if we can refer to those terrible wars, squabbles. So the Helen of geometry, this is a double-edged kind of epithet, because another thing that happened with this beautiful curve, lots of people argued about who'd done what first and whose methods were best. Descartes wrote this very scathing letter about Fermat's attempts to understand tangents to the cycloid. He said it was ridiculous gibberish, which is not the referee's report you want to receive. But it's got lovely properties. I'm just going to tell you two properties that it has that are great. Very simple formulas for the area and the length. So the area under that arch is exactly 3 times the area of the circle that makes it. Lovely. The length of the arch is exactly 4 times the diameter of the circle that makes it. Really, really nice and simple things. And there's another lovely thing about the cycloid, which sometimes happens in mathematics. You see something cropping up in an area you weren't expecting. I'm going to let Ishmael tell us about this. So Ishmael is on his whaling ship. He has to clean out these big cauldron-like vessels called tripods. He says it's a place for mathematical meditation, like everywhere. He's in the left-hand tripod of the Pequod, the ship. The soapstone diligently circling around me, he says, that I was first indirectly struck by the remarkable fact that in geometry, all bodies gliding along the cycloid, my soapstone, for example, will descend from any point in precisely the same time. So what he's referring to there, just as an aside, just a lovely little mathematical aside in the middle of the ocean, is this very famous mathematical problem called the tortichrome problem, which feels like it shouldn't have a solution. Feels like too much to ask of any curve. But the question is there some curve that exists so that if you've got you make it and then you release some particle somewhere on the curve and let it go, doesn't matter where you release it from, it reaches the bottom in the same time. Feels like, how could that be true? If it's up here and there's one down here, surely this one will get there first. But then maybe the one up here is going faster because it's got more potential energy, it picks up more speed. But there's no guarantee there's going to be even a solution. But guess what there is? And it's the cycloid. And it kind of unexpectedly, because we looked at it rolling wheels along roads, right? And here it is in this other situation. So it's really fabulous, and it's so great to just see it dropped into Moby Dick. So this is a kind of metaphor. We're going to finish with one final example of how mathematics can make itself known in literature, because every so often the mathematics comes out into the open, and you get a book that actually talks about mathematics in the book as part of the plot, and even sometimes a mathematician character or two. So I'll just finish with this kind of, it's not quite as much of a great American novel as Moby Dick, but it's the end of the lecture, so let's relax a bit. Jurassic Park. So it's a fun read. Even if you haven't read it, you probably know roughly the plot of Jurassic Park. Bad guy scientists decide to open a dinosaur theme park, and it doesn't end well. Okay, that's the précis. In this book, there's a mathematician character. I've got 1 minute. It might turn into 3 minutes, and there's nothing he can do about it. So I've got the microphone. In this book, there's a mathematician character called Ian Malcolm. And in the films, he's played with someone with absolutely normal standard levels of charisma for a mathematician. It's Jeff Goldblum. Totally not any math department in the country. It's fine. So he's there to say, look, because of chaos theory, right, sufficiently complex systems, we lose the power to predict, because little changes, fluctuations in the initial conditions, and magnify until you lose the power of prediction, you don't know what's going on. In the book, there's an extra little layer of this, another little mathematical metaphor, which is the book is divided into 7 sections. They're called iterations, suggestively, and each of them feature a diagram that changes and grows as the book continues. And this is how you make this diagram. So you take a piece of paper, you fold it in half, unfold it. You've got like a bent piece of paper now, but then you do it again with 2 folds, unfold, you've got a zigzag. Do it again with 3 folds, and you get a slightly more complicated picture. Then on the right there, that's 4 folds. At some point, your paper isn't really working, so you move to a machine and get the machine to do it. And then you can do this on a machine by just saying any straight bit now, at the next iteration becomes an L-shaped bend. And you look at this and you think, okay, I don't really understand, but maybe given an afternoon, I could work this out and kind of get a formula and know what this is going to look like. So you feel you're lulled into a false sense of security, right? These are the pictures that appear at the beginning of the chapters or the iterations of Jurassic Park. So this is kind of continuing on this step. He starts at step 4 because the first few are a bit boring. First iteration is there. Then second iteration, same process, doing exactly the same, very, very simple thing. Folding paper. Third iteration is there. And then 4, 5, 6, 7, right? That, if you've not seen this before, I will bet you that you wouldn't predict that just as simple folding a piece of paper in half can get to this amazing thing, which is an example of a fractal. It's got this fabulous self-similarity properties. You see smaller copies of the thing within the whole. It's incredibly complex, unpredictably so, and it's a fabulous metaphor for how, yeah, we may have unexpected complexity in something we thought we understood. So to finish off then, I will just give you this warning from literature that if you don't listen to mathematicians, you will probably get eaten by a velociraptor. Okay, I'll stop there. Thank you.
Thank you for an excellent, wonderful talk. We have time for a few questions. If anybody has any questions.
What's my favorite book? Okay. Oh golly. What's your favorite child? I mean, it's a tricky one. It will of course vary according to what I'm my mood. I mean, Moby Dick was in my top list for a while. I'm having a big I love A Gentleman in Moscow phase by Amor Towles. That's a really fabulous book. When I was 7 years old, my favorite book was Lord of the Rings, and no one can judge me for that because it's very cool. So yeah, it varies. What's your favorite book? There you go, you see, shoes on the other foot, yeah. Yeah, okay, yes. What's the value of S? So that this was S, the shortest chapter in the Luminaries. What is the value of S? So in words, 95. So I don't absolutely know whether was she doing letters or characters, but it's 95 words, which does, if you quickly multiplying that by 2048, the book is over 800 pages long, The first chapter is therefore over 400 pages long. So but in fact, even if that final chapter is only one word, it's quite an ask to do this. And you can work out what's the longest possible book, right? What's the highest number of chapters you could possibly get with this structure, with doubling and doubling and doubling, to be able to bind a book that would just fall apart. And I reckon it's 18 chapters and the last chapter is one word. But, yeah, publishing technology may advance, make it more possible. Nice one.
It seems to me that all these samples came up from Western literature. Do you know if anyone has looked into non-Western literature?
Yeah, so I had a little, sorry, yes, repeat the question. So examples I gave are from Western literature mainly, and so have people done studies into this kind of thing in non-Western literature? So firstly, define Western. So yeah, that's one thing we could talk about. But certainly I've looked at Korean folklore and fairy tale because I was invited to go and give a talk in Korea. And I thought, I can't just go on about threes if there aren't any threes in Korean folklore. So I did have a look at that. And in Korean folklore I'm not an expert, you get threes, but you also get fives. And actually that's true in Chinese mythology as well. So you get fives, and it's kind of the 4 points of the compass that we would think about. Actually, there's 5 because you're being in the middle. So there's this kind of fiveness that happens, and that can sometimes be extended to 8s with a 1 in the middle, so like 9. And so there's this very famous Korean book called The 9-Cloud Dream, which involves this young man going on a journey, and he meets these 9 young women, and various things happen. And so there are 9s there, and that's reflected in also a lot of the religious imagery. So that there are different numbers that have different resonances in different cultures. I still think, though, that 3 does have this particular power. And in fact, it's broader than literature because very many areas, disciplines have a rule of 3. Like if you're talking to anyone, I say, oh yes, there's one of those in architecture, there's one of those in interior design, there's a rule of 3 in comedy. So I think 3 does have a special role, but then the other things have cultural differences. But yes, certainly I think there's a lot more that can be said about all kinds of literature. So yeah.
Time for maybe 1 or 2 more questions.
Yeah, and then obviously there's this reception. So. There's. Oh, right. So the words in a Sanskrit poem, there's a Fibonacci sequence link. So, I mean, the thing I know about is kind of the rhythmic patterns. Is that what you mean? So yeah, this is very cool difference between kind of typically poetry in English. When we're thinking about the meter, you have stressed and unstressed syllables. So if you think, well, how many possible meters are there of, I don't know, 4 syllables, right? Well, the first one is stressed or unstressed. So it's 2 times 2 times 2. You get powers of 2 for the number of possibilities. But in the Sanskrit tradition, in order to sort of say that this is a stressed syllable, you make it last longer. And traditionally, the stressed syllables, which are called guru, last twice as long as the unstressed lagu syllables. And that, you work out like what are the possibilities there, you get the Fibonacci sequence. And the reason you get it is because if you're trying to make like the next collection long, you know how many there are of 1, 2, 3, 4, and 5 syllables. Right, to get 6 syllables, you can either take a 5-syllable meter and add a short lagu to it, or you can take a 4-syllable meter and add a long guru to it. And so it's exactly the recursion that you get with Fibonacci. So yeah, the Fibonacci numbers arise just naturally in the study of Sanskrit meter. And they were therefore being studied in that context centuries before Mr. Fibonacci came along and brought them to the West, yeah.
So I think we should probably postpone any further questions. If you have other questions for Professor Hart, please come to the reception in the Hendricks Center and mob her with extra questions. But first, let's give her a proper round of applause.
Thank you.